the Laplace transform. So this section will introduce the concept of the Laplace transform and show how to find the Laplace transform for certain types of functions. It's another tool that we can use to solve initial value problems. And what it does is it changes a differential equation into an algebraic equation. We solve an algebraic equation using algebraic techniques, and then we have to undo the transform to get back to the solution. And we'll see that idea, the solving an initial value problem, that's a couple sections away. Right now we got to start by introducing the idea behind it and see some examples of how we find that transform. The Laplace transform is what's called an integral transform. What it does, and what a transform does, is it eats a function. Its input is a function. It does something to the function and it outputs a function, but in a new domain. Sort of like how a function takes an input of a number and outputs a number, a transform takes a function as the input and outputs another function. When you learned how to find derivatives, derivative is really a transform. It takes a function, does something to it, and you get a new function out of it. The derivative is a transform. And the Laplace transform is just a transform. And it's defined as follows. If we have some function f of t and it's a piecewise continuous function, right, it's got to be piecewise continuous, then the Laplace transform of f is given by this. And so the Laplace, so there's, right, this notation, right, the Laplace transform of f of t, right, that's the notation for that. The Laplace transform of f of t is given by this integral. And notice that this integral goes from 0 to infinity. It's what we called back in calculus an improper integral. And we have this improper integral from 0 to infinity of e to the negative st times f of t dt. We're integrating with respect to t. We're substituting the 0 and infinity and subtracting, and we will get, if this exists, right, if this integral exists, if it converges, we get this new function, which we will call capital F of s. So one thing that's important, our original function is in the t domain. We apply the Laplace transform, we get a new function in the s domain. And I mean, those letters aren't important, but they're generally what are used. T, and then we apply the Laplace transform, we get a new function in s. So now let's see some examples of finding the Laplace transform. Let's find the Laplace transform of 1. So then, by definition, this is equal to the integral from 0 to infinity of 1 times e to the negative st dt. Now, back in calculus, you learned to, rewrite this as a limit, right? Substituting and getting rid of the infinity and changing it out with some other letter, and then taking the limit at the end. I'm just going to substitute the infinity at the end, and we'll talk about what happens if we have that infinity. Alright, so we're integrating 1 to infinity, 1 times e to the negative st dt. Well, that's just the integral from 0 to infinity of e to the negative st dt. Now remember, we're integrating with respect to t, so s is just s is a constant. And so if we use a simple substitution here, this is the same as negative 1 over s e to the negative st from t equals 0 to t equals infinity. So the negative 1 over s is a constant, negative 1 over s, and I would have e to the negative s times infinity minus e to the negative s times 0. Now let's think about this. Well, e to the negative s times 0, well, that's just e to the 0, so that's 1. But now what happens here? What's e to the negative s times infinity? Well, remember, that's the same as, right, so this this is the same as 1 over e to the infinity. And if you remember how, that's basically 1 over a large number, and so that's 0. Right, that'll tend to 0 as t gets closer and closer to infinity. All right, so something to remember, right, in general, remember that e to the t approaches 0 as t approaches negative infinity. All right, so what do we have now? All right, so then the Laplace transform of 1 is negative 1 over s times 0 minus 1, and so then this simplifies as 1 over s. So the Laplace transform of 1 is 1 over s. And we know how to find the Laplace transform of 1. Okay, so now let's up the ante a little bit. Let's find the Laplace transform of t. Well, this would be the integral from 0 to infinity of t e to the negative st dt. So I have an algebraic factor, t, and a transcendental factor, e to the negative st. So this might remind you to use maybe an integration by parts. And so, we would say, okay, let u equal t, let dv equal e to the negative st dt, then du is equal to dt, and v would be negative 1 over s e to the negative st, and we apply integration by parts, and then we go from there. Now, another approach to this is what's called a tabular integration. And so we built a little table here. We start with the t and the e to the negative st. And on the left-hand side, we differentiate. T, derivative is 1, derivative is 0. When you get to 0, you're golden. E to the negative st, you integrate that. Negative 1 over s, e to the negative st. You integrate that again. 1 over s squared, e to the negative st. And then what you do is you multiply diagonally. Multiply, multiply, and every other one you add in a negative. So what this then tells me is the Laplace transform of t, applying the integration by parts, I would have t times negative 1 over s e to the negative st, and then I'm going to have a minus 1 times 1 over s squared e to the negative st. And that'll be, again, from 0 to infinity. And once you have the 0, you stop. Okay, so there isn't going to be a third line here, a third multiplication. All right, so now substituting infinity and 0. So let's see, I would have, letting t go to infinity, let's see, I'd have an infinity, I'd have a negative 1 over s, and then I'd have an infinity over e to the negative infinity minus 1 times 1 over s squared e to the negative infinity minus, now substituting 0, I'd have 0, well, I'd have a negative 1 over s again, I'd have a 0, and then I'd have an e to the negative s times 0, and then I'd have a minus 1 times 1 over s squared e to the 0. Alright, so what happens here? What is it? This infinity over... Alright, I shouldn't have written it like that. I should have written it as infinity times e to the negative infinity. There. So now what happens here? What's infinity over e to the negative infinity? Well, e to the negative, so let's look over here. What happens here? This is infinity over e to the infinity, isn't it? And e to the infinity is larger than just infinity, and so this will tend to 0. Now, officially what we should have said is, what's the limit as t approaches infinity of t over e to the t. And applying L'Hopital's rule, that would be the limit as t approaches infinity of 1 over e to the t, which then goes to 1 over infinity, which is clearly 0. That's the official way. Alright, so let's see, what do we have now? We would have 0 minus, and remember, it's this e to the negative infinity here, that's going to tend to 0. So we have 0 minus 0 minus, let's see, I have negative 1 over s squared times, hey, there's a 0 here, so that's going to be a 0 minus 1 times 1 over s squared. Now, e to the 0 is 1, so that would be a 1 over s squared. And so after we simplify all this, we get that the Laplace transform of t is 1 over s squared. So we know how to now find the Laplace transform of t, and we're going to go to the next one. So now let's find the Laplace transform of t squared. And this would be a good opportunity for you to pause and try this one out on your own. Alright, from the definition, the Laplace transform of t squared would be the integral from 0 to infinity of t squared e to the negative st dt. Now, if you remember from Calculus 2, if we were to evaluate this integral, the antiderivative of t squared e to the negative st, we'd have to apply integration by parts twice. Now, if we use that tabular integration technique, I would start with t squared and e to the negative st, and I would differentiate t squared. So that's a 2t, differentiate 2t, that's 2, and differentiating 2, that's 0. Alright, so we'll stop there. Let's antiderivative on the other side, negative 1 over s, negative just 1 over s, e to the negative st, 1 over s squared, e to the negative st, negative 1 over s cubed, e to the negative st. Alright, and then we're going to multiply, 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 throw a negative on that one. Alright, so every other one you throw in a negative. So then we would have that this is negative 1 over s t squared e to the negative st minus 2 over s squared t e to the negative st minus 2 over s cubed e to the negative st, evaluated from 0 to infinity. Alright, now let's think about what's going to happen if we substitute infinities. Alright, let's focus on this term here. We have this t squared e to the negative st as t approaches infinity. So the limit as t approaches infinity of t squared e to the negative st, well, that's the same as the limit as t approaches infinity of t squared over e to the st, and that's infinity over infinity. We apply L'Hopital's rule. That's the limit as t approaches infinity of 2t over derivative s e to the st. That's still infinity over infinity. We apply L'Hopital's rule again, and now it's the limit as t approaches infinity of 2 over s squared e to the st. And now that's 2 over infinity, it goes to 0. So evaluating at infinity, I've got an infinity, right, so evaluating this term at infinity, that's going to go to 0 minus evaluating the t e to the negative st as t approaches infinity. Again, that's going to give us a 0, like in the previous exercise, minus, and here we have a term with an e to the negative st as t approaches infinity. That's also going to give me a 0. Now, substituting t equals 0. Well, if I let t equal 0, right there, that's going to give me a 0. Similarly, I'll get a 0 for the second term, and then let's see, in the last term, I have no factors that'll go to 0. So I'll have a minus 2 over s cubed, and e to the 0 is 1. And so, simplifying all this, we get that the Laplace transform of t squared is 2 over s cubed. And we could go on further with this. We could find the Laplace transform for higher degree terms. I'll just state the rule in general. In fact, a general rule is for whole numbers n, the Laplace transform of t to the n is given by n factorial over s to the n plus 1. And so, for example, the Laplace transform of t to the 6th would be 6 factorial over s to the 6 plus 1. 6 factorial is 700. So remember, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And so then that's 720 over s to the 7th. So we have a rule that we can use to find the Laplace transform if it's just t to a whole number power. And it turns out to be take the power factorial over s to the power plus 1. You don't have to memorize this formula. I'm going to give you a formula sheet that you're going to be allowed to use on all quizzes and tests, but you have to be able to use it correctly. Alright, so let's build another formula. We want to find the Laplace transform of e to the at. And let's assume that s, alright, that's s that we're using, let's assume that s is greater than a, which implies that s minus a is greater than 0. We'll make that assumption. We're going to need to use that later, so we'll make that assumption. So then the Laplace transform of e to the at from the definition is the integral from 0 to infinity of e to the at times e to the negative st dt. And if you recall some properties of exponents, since we have the same base e, we would then add the exponents. So then this is the integral from 0 to infinity of e to the a minus s times t dt. Well, that's the same as writing the integral from 0 to infinity of e to the negative s minus a t dt, right? You can check the signs there. So now s minus a, we're just going to treat as a number because we're integrating with respect to t. And so the antiderivative would be negative 1 over s minus a e to the negative s minus a t, and we would evaluate that at 0 and infinity. Alright, now letting t equal infinity. Alright, so remember then 1 over s minus a is a constant, and really I can't forget that negative. We have negative 1 over s minus a. Now substituting infinity, then I would have e to the negative s minus a times t. So I'd have e to the negative s minus a times infinity. Well, since s minus a is greater than 0, then this term here is going to go to 0. Minus, substituting 0, e to the negative s minus a times 0. And that term, right, that's e to the 0, this term is going to go to 1. So I now have negative 1 over s minus a times negative 1, and so then this tells me that the Laplace transform of e to the at is equal to 1 over s minus a. Alright, so we'll add that. That's going to be on our formula sheet also. The Laplace transform of e to the at is 1 over s minus a. So for example, if I wanted to find the Laplace transform of, how about the Laplace transform of e to the 7t? Well, then the Laplace transform of e to the 7t, it fits this form, and so then this would be 1 over s minus 7. And if I had the Laplace transform of e to the negative 4t, the Laplace transform of e to the negative 4t would be 1 over s minus negative 4. We don't leave it like that. We'll write that as 1 over s plus 4. Alright, so what if we can find the Laplace transform of a function, f of t, but now that function is being multiplied by some constant, some number c. So let's find the Laplace transform of c times f of t. Well, from our definition, this would then be equal to the integral from 0 to infinity of c times f of t times e to the negative st dt. And if you remember your rules for integrals, this constant, that c, we can bring that outside the integral. So then this is equal to c times the integral of 0 to infinity of f of t e to the negative st dt. Well, this whole thing, right, this integral from 0 to infinity of f of t e to the negative st dt, that's just the Laplace transform of the function f of t. And so then what this tells us is the Laplace transform of c times f of t is c times the Laplace transform of f of t. What that means is, if we have a constant multiplier, right, if we're multiplying some function by a constant, we can sort of bring the constant outside of the Laplace transform. Useful tool. Now also, we have this concept of linearity. What that means is, if we are adding or subtracting functions inside and we want to find the Laplace transform, we can break it up into multiple Laplace transforms. And so what we'll say is the Laplace transform of c times f of t plus, say, d times g of t. Right? So if we have multiple terms and we need to find a Laplace transform, we can break that up. And so then this is the same as c times the Laplace transform of f of t plus d times the Laplace transform of g of t. So it allows us, we're allowed to break it up. I mean, basically because it's just an integral. So all of our rules for integrals that we learned back in Calculus 1, they still apply here. So let's see an example. Suppose I wanted to find the Laplace transform of, let's do something nasty, the Laplace transform of 7t to the 4th minus 9t squared plus 6e to the 3t. I need the Laplace transform of this thing. Alright, applying the linearity concept then, this would be 7 Laplace transform of t to the 4th minus 9 Laplace transform of t to the 2nd plus 6 Laplace transform of e to the 3t. And I threw in a negative there by mistake. Oops, sorry about that. I don't know what happened there. Let's erase that negative. Alright, so then this is 7 times, now the Laplace transform of t to the 4th, we learned earlier that that would be 4 factorial over s to the 4 plus 1 minus 9 times the Laplace transform of t squared, that's 2 factorial over s to the 2 plus 1 plus 6 times the Laplace transform of e to the 3t, that's the most recent rule we saw, that's 1 over s minus 3. So then this, let's see, 4 factorial is 24, 7 times 24, that's 168 over s to the 5th, 2 factorial is 2. 9 times 2 is 18, minus 18 over s cubed, and plus 6 over s minus 3. So once we've built these rules, we can use them instead of going back to the definition. Just like once you learned rules for derivatives, you didn't have to go back to the limit definition of the derivative. You were allowed to use the rules to find derivatives. Same thing here. Once we learn the rules for Laplace transforms, we don't have to go back and use the definition unless we're told to, or unless it's a new situation that we don't know how to deal with yet. So now let's mention something about notation with the Laplace transform. So we've seen that this Laplace transform, it takes a function from the t domain and it brings us over to the s domain. So some notation that we use for it. So if we have a function in the t domain, we have some other function in the s domain, and the Laplace transform is what gets us between these, right? We have this Laplace transform. So the function in the t domain, what we usually use is we usually use lowercase letters for the function in the t domain. And so then for the function, the corresponding, the Laplace transform in the s domain, we usually use capital letters. So I would use capital F of s. Or sometimes I'll just simply use just capital F, with the understanding that it's now a function of s. Similarly, y of t, I would use capital Y of s, or simply just capital Y. X of t, capital X of s, or simply x. Got to be careful with those, right? Because my x's tend to look similar, both lowercase and uppercase. So got to be careful when we mention those. Okay, so that's important that we understand which it is. So we'll use the convention that lowercase is the t domain, uppercase will be the s domain, and is the Laplace transform. So now let's find the Laplace transform of the derivative of the function f of t. So what's the Laplace transform of f prime of t? Well, let's go back to our definition because we haven't learned how to deal with this yet. So the Laplace transform of f prime of t would be the integral from 0 to infinity of f prime of t times e to the negative st dt. And we're going to use integration by parts. And what I'm going to do is I'm going to let u equal e to the negative st, and I'm going to let the dv equal f prime of t dt. So then the du would then be negative s e to the negative st, and then v, the antiderivative of f prime of t, is just f of t. Alright, so applying integration by parts then, this would be equal to uv e to the negative st times f of t minus the integral of v du, minus the integral of f of t, that should be a dt there, times negative s e to the negative st dt. And we need to, right, and so then this would be from 0 to infinity, and this would be from 0 to infinity. Alright, so now let's clean this up a little bit. So then this is e to the negative st times f of t from 0 to infinity. And notice now I can bring this s outside the integral, so that's plus s times the integral from 0 to infinity of f of t e to the negative st dt. And if you look at this integral from 0 to infinity of f of t e to the negative st dt, well, that's just the Laplace transform of f of t, which I'll write as capital F of s. Now, what about this other thing here? I've got this e to the negative st f of t at infinity and e to the negative st f of t at 0. So here we have to be a little careful. We know that e to the negative st goes to 0 as t goes to infinity. But we don't know what the function f of t is. So what we're going to do here is let's assume that f of t is of what's called exponential order. What that means is the function is less than some exponential function. It's of exponential order. And if under that assumption, then e to the negative st f of t will also go to 0 as t approaches infinity. So then what do we have? We would then have 0 minus e to the 0 f of 0 plus s times f of s. And so we normally write this as, so then what we have, the Laplace transform of f prime of t is then s times capital F of s, s times the Laplace transform of s, and then minus e to the 0 is 1, so minus f of 0, the original function evaluated at 0. And so now let's find the Laplace transform of the second derivative of f of t. Maybe you want to try this one on your own. That would be a good time to pause. Using the definition, this is then equal to the integral from 0 to infinity of f double prime of t times e to the negative st dt. We'll use integration by parts again. And so we'll use u equals e to the negative st, du is negative s e to the negative st dt, and dv is f double prime of t dt, and so then v is f prime of t. Just f prime of t, no dt there. So then using integration by parts, I would have, let's see, uv e to the negative st times f prime of t from 0 to infinity minus the integral from 0 to infinity of v du f prime of t times negative s e to the negative st dt. Alright, so let's see. E to the negative st f prime of t 0 to infinity. And now again we'd have plus s integral 0 to infinity of f prime of t e to the negative st dt. And now we're going to use a trick just like we saw in the previous exercise. Notice that this right here, the integral from 0 to infinity of f prime of t e to the negative st dt, hey, that's just the Laplace transform of f prime of t, which we saw in the previous exercise. The Laplace transform of f prime of t ended up being s times f of s minus f of 0. So now let's see what happens here. Substituting infinity, and again, if we assume that the function is of exponential order, its derivative will be of exponential order. And so this ends up being 0. Substituting infinity, we'll get a 0. Minus, substituting 0, we'll get f prime of 0. And then I have plus s times s f of s minus f of 0. Simplifying this, we find that the Laplace transform of f double prime of t is s square f of s minus s times f of 0 minus f prime of 0. Now, as you might imagine, if we wanted to find the Laplace transform of, say, the third derivative, we'd use integration by parts, and we'd end up with something in terms of the second derivative, which we've now defined. And so this is, basically, it's a recursive definition, or a recursive process. We can find the Laplace transform of the next derivative by using the result of the previous derivative. And unfortunately, people before us have figured this out as well. And so we have, here's some notation, here's a general rule that we can use. And here's what it says. The Laplace transform of y, the nth derivative of y of t. So if we want the Laplace transform of the nth derivative, now I don't have this one memorized, so I'm going to copy it from our sheet. The derivative, the Laplace transform of the nth derivative of y of t, we end up with s to the n times capital Y of s. S to the n times the Laplace transform of y minus s to the n minus 1 times y of 0, lowercase y of 0, minus s to the n minus 2 times y prime of 0, minus, and then we would have an n minus 3 and a y double prime, and we keep on finding multiple terms until basically we get to the last term, and the last term would be the n minus first derivative of y evaluated at 0. So let's see a quick example using this formula. Let's find the Laplace transform of the fourth derivative of f of t. Alright, so the Laplace transform of the fourth derivative of f of t, well, following the rule, so now following this pattern, and I just have an f instead of a y. That's the only difference. So then this would be s to the fourth, n is 4, times capital F of s, minus s to the n minus 1. 4 minus 1 is 3. S third, lowercase, so the regular function, the function evaluated at 0, minus s to the n minus 2. N is 4. 4 minus 2 is 2. S square, f prime of 0, minus s to the first, f double prime of 0, and then minus, finally, now our last term would be f triple prime at 0. And so there's the Laplace transform of the fourth derivative of f. So let's finish off this section with a more complicated example. Here our function is not a standard function. It's not a nice algebraic function maybe. Here I've got this piecewise defined function. I have the function that's defined as 0, where t is between 0 and 2, and then it's defined as 1, where t is greater than 2. So let's draw. Let's make sure we understand what this is saying. So if there's my axes, right, and here's the t-axis, and so here's 1, and here's 2, and here's 3, and 4 on the t-axis, and here's 1, and here's 2 on the f of t axis. And I'll draw the function, how about in something that's nice and bold? I'll draw it in this blue highlighter. Okay, so the function is 0 as long as t is between 0 and 2. So it might look something like this. There it's 0, but then at 2 it jumps to 1 and then continues on to the right. So here's that function, and we want to try we got to find the Laplace transform of this function. Well, our general rule says that the Laplace transform of our function f of t is the integral from 0 to infinity of f of t e to the negative st dt. But our function changes rules in the middle. So what I'm going to do is I'm going to break up this integral into two integrals. I'm going to write this as an integral from 0 to 2 of f of t, e to the negative st dt, and then the integral from 2 to infinity of f of t, e to the negative st dt. Now over the interval 0 to 2, f of t is 0. And over 2 to infinity, f of t is 1. So then this becomes the integral from 0 to 2 of, well, what's 0? 0 times e to the negative st, that's 0 dt. And then we have the integral from 2 to infinity of e to the negative st dt. Well, integrating 0 over any interval is 0. So this is 0 plus, and the antiderivative of e to the negative st, that's a negative 1 over s, e to the negative st from 2 to infinity. Substituting infinity, we get a 0, so that's negative 1 over s. I have a 0 and a minus e to the negative 2s. So then this ends up being e to the negative 2s over s. So if we have a function that is a piecewise defined function, we might need to go back to the definition and go from there, breaking up our integral into multiple integrals and evaluating. We'll actually see a different approach for evaluating this integral in a later topic. Evaluating this Laplace transform. We'll see another approach for it later on in the course. Alright, so that ends our introduction to the Laplace transform and how to find them. In the next section, we're going to say, okay, what if we need to undo that? How do we invert this process? How do we undo the Laplace transform? Turns out to be not that bad, as long as we know how to use a table. Alright, see you then.